Hi everyone, in this video I'm taking a look at question 8 part D of the 2011 Extension 2 HSC exam. This part D says to let function Sx be equal to the sum from k is equal to 0 to n of ck times x plus 1 on x all to the k, where the real number ck satisfy the magnitude of ck being less than or equal to the magnitude of cn for all k less than n, and we're told cn is not equal to 0. So the question is, using part C or otherwise, show that Sx equals 0 has no real solutions. And so we're given this link to use the results in part C. So I've got part C displayed here as well. I actually worked through part C in a separate video. So if you haven't already taken a look at that, it's probably worth taking a look because the result in that part C, particularly C part 2, is going to be helpful for us here. So yeah, let's take a look. So I've written out the key pieces of information from this question, including some of the key elements from part C, given we were provided with the hint to link up with part C. So I think in terms of what technique is going to help us here, it's often the case that when you're asked to prove something about the roots of a polynomial, in this case we're asking to prove no real roots. You may see other questions that ask you to prove something like no rational roots. In those kinds of questions, often proof by contradiction can be a good technique, because what you can do is you can assume the opposite. So here we're trying to show no real roots. So let's assume there is a real root and then see if it leads somewhere that can't be true, some kind of contradiction. Because from there you can then conclude that the opposite must be true. So here we're going to use proof by contradiction, and the setup to all contradiction proofs is to assume the opposite of what you're trying to show. So here let's assume alpha is a root of Sx and alpha is real. So that's our setup. So we've got this real root of Sx, even though we're trying to show there aren't any. Now from there, I think the approach, the strategy that we can take in carrying out this proof is to try and link up this function Sx with pz that we were looking at in part C. And you can kind of see that with a few little transformations we can get there, because fundamentally the function Sx is the sum of a bunch of things, just like pz, it's the sum of a bunch of things. And it's got a power that's going up from 0 to n. Here we've got z to the 0, z to the 1, z to the n minus 1, and so on up to z to the n. Here we've got the same thing, it's just x plus 1 on x to the 0, then to the 1, and so on up to the n. So if we can kind of create that direct link, we'll then be able to make use of these results, and in particular this one here, that hopefully will help us show something nonsensical mathematically so that we can say this can't be true. So I think the first step to kind of lining these two functions up is to kind of simplify this x plus 1 on x into just a z that we can kind of directly compare. So let's do that. Let's let z equal x plus 1 on x, so that therefore we can say that s of z in this case, because now we're going to deal with the z, would be equal to the sum from k is equal to 0 to n of ck z to the k. Or in other words, if we expand that out, we'd get c0 z to the 0 plus c1 z to the 1, and so on up to cn minus 1 z to the n minus 1 plus cn z to the n. And you can start to see just how similar these two functions become. Still a bit of work to do though, because we kind of don't have anything in front of the z to the n, whereas here we do. So there's going to be a bit of tweaking required, but basically we're off to a good start. I think the next step to try and make this link is to assume a root of this function sz, and then kind of try and show this outcome here, that root, whatever it is, will be in this format, so that then we can apply this result. So maybe it would make sense to define this root as beta, given we're trying to show a similar thing. So let's let beta be a root of sz, and given z is x plus 1 on x, beta is essentially whatever value of z will set this to 0, and given we know setting x is equal to alpha gets the whole thing to 0, we can therefore say that beta must be equal to alpha plus 1 on alpha. That's the kind of format of beta. So at this point I might turn over, but essentially we can insert beta into this function and set it to 0. So let's turn over and do that. So we can say, therefore, c naught beta to the naught plus c1 beta to the 1 and so on, plus c n minus 1 beta to the n minus 1 plus c n beta to the n is equal to naught. Now, it might be helpful just to rewrite this in the same order that we had pz written in, with the z to the n first, just to help with drawing the comparison. So let's just do that as a step. So let's say we've got cn beta to the n plus cn minus 1 beta to the n minus 1 plus, and so on, c1 beta to the 1 plus c naught beta to the naught. Anything to the naught is just 1, so plus c naught, that's all equal to 0. And as I mentioned before, we don't want anything in front of this first term because we don't have anything in front of it for our pz function. So to get rid of that, we can just divide both sides by cn. That'll do it. And we can do that without having some kind of division by 0 issue, because we're expressly told that cn is not 0. And that's kind of, it's now clear why we had to be told that in the question, because it's almost like they're hinting you're going to have to divide by this thing somewhere, so we better tell you it's not 0, so it's okay. So we'll divide both sides by cn, so we'll get cn on cn beta to the n plus cn minus 1 on cn beta to the n minus 1 and so on, plus c1 on cn beta plus c naught on cn is equal to 0 on cn, which will just stay as 0. So these cn's will cancel, which is what we wanted. So we end up with beta to the n plus cn minus 1 on cn beta to the n minus 1 and so on, plus c1 on cn beta plus c naught on cn is all equal to 0. And we're looking pretty good now. We're quite close. We've got our betas from n all the way down to beta to naught, and something in front of each of them. Now, again, if we really want to draw this link, it might be helpful to just have our coefficients of betas be something like a, just a n minus 1, a1, and so on. And so to do that, we can just define it. We can just let ak be equal to ck on cn, because according to that definition, we can then just replace each of these c something on cn with just a. So therefore what we can say is that we'll have beta to the n plus a n minus 1 beta to the n minus 1 and so on, plus here it's 1, so we'll have a1 beta plus a naught is equal to 0, and that is exactly the format that we had here. So we've kind of shown the equivalence of this function we're dealing with and the function we dealt with in part C. And so what we can do is we can conclude, therefore, we can say something along the lines of the roots of this function sz are equivalent to, maybe I'll just write it like this, equivalent to the roots of the function pz that we dealt with in part C. And so therefore we can conclude that the absolute value of beta, this root of sz, must be less than 1 plus m, because that is what we showed to be true when dealing with an equivalent function in part C. So I guess now we've got to think about, well, what is m, capital M, for this function sz? And that's where this extra information we were given kind of now starts to become relevant, because remembering that m is the maximum of all these coefficients, the magnitude of all the coefficients, which we've got here still these coefficients, but here we define our coefficient as ck on cn, and we're told that basically for all of our ck's, the maximum value will be cn, because they're always less than or equal to that cn value. So I guess we can say something like, since the absolute value of ck is less than or equal to the absolute value of cn, it follows that m, our maximum coefficient, must be the magnitude of cn on cn. That's what's going to give us our maximum coefficient, and that is just the magnitude of 1, which is just 1. So if we know that m is 1, we can therefore conclude that our magnitude of beta must be less than 1 plus 1, or in other words, it's less than 2. And I think from there we can now see whether, if this is true, do we end up with something nonsensical? Because remember, we're trying to do a proof by contradiction, and so we want to see, when we assume we've got this root alpha of our original polynomial, and we assume that's real, do we end up with something silly? So let's maybe turn over, and let's now make the link between beta, which must be less than 2, and what format beta is in, which is alpha plus 1 on alpha. So let's substitute that in. So let's say, therefore, the magnitude of alpha plus 1 on alpha must be less than 2. And here we can just, I think, as long as we're careful, do a bit of manipulation, and I think we're going to get what we need. So this absolute value, we go right back to the definition of absolute values, it's the square root of whatever we've got inside the absolute value squared. So it'll be the square root of alpha plus 1 on alpha squared, less than 2. And so now we can square both sides to get rid of this square root. And so we'll end up with alpha plus 1 on alpha squared is less than 2 squared, or less than 4. It's probably worth getting a common denominator here. So we'll have alpha squared plus 1 on alpha all squared is less than 4. And if I just square top and bottom, we'll have alpha squared plus 1 squared on alpha squared is less than 4. And now at this point, I'm going to move up this alpha squared. And it might seem like a fairly innocuous step, but it's actually, this is now the essence of our assumption that alpha is real. Because if we want to maintain this inequality, the direction, we need to know that what we're multiplying is a positive number. Now, for all real numbers, when you square a real number, you know it's positive. But that's not true with complex numbers. And so if alpha could have been complex, say alpha is equal to I, well, we know I squared is negative 1, and if we wanted to multiply that up, we'd have to reverse the direction. So actually assuming alpha is real is really important for this particular step. And I suppose if you hadn't expressly stated that alpha is real and you tried to do this, maybe a harsh marker might say, you know what, you don't necessarily know what you're doing, and maybe they'll take off marks. So we'll say, since alpha is real, alpha squared must be greater than 0. So therefore we can say alpha squared plus 1 squared will be less than 4 alpha squared. And maybe here we can just expand this and bring everything over so we've got a 0 on one side, because often inequalities are easiest to deal with when there's a 0. So this will be first 1 squared, so alpha to the 4, plus twice the product, so 2 times 1 times alpha squared, plus the last 1 squared is less than 4 alpha squared. So now I can subtract over this, and 2 minus 4 will be minus 2. So we'll have alpha to the 4 minus 2 alpha squared plus 1 is less than 0. And here this is actually something that we can factor back as alpha squared minus 1 squared is less than 0. And that's because alpha squared minus 1, if we were to expand that, we'd have the first 1 squared, or alpha to the 4, minus twice the product, or minus 2 alpha squared, plus the last 1 squared, or plus 1. And here we have it. We've come to our contradiction, because if alpha is real, as we've assumed, then alpha squared minus 1 squared, well, anything real squared has to be positive. We've just made use of that. But we're saying, no, it's negative, which is a contradiction. So therefore, we've got a contradiction. Since maybe we can just say, maybe if I just put it as generic of x squared is greater than, it must be greater than 0 if x is real. Like that's kind of what we know to be true, yet we're saying it must be negative if we've followed along mathematically from our starting assumption, which was that alpha is real. So given we've got that contradiction, we can say therefore alpha is not real, and therefore s of x, being the function for which we assumed alpha was the root, must have no real roots.
Panic boom!
And that's it. That's how you can tackle that question. So actually, on reflection, it's a pretty tough one. You can imagine plenty of students would not get there. We're told to use the link to part C, but I'd argue it's not an obvious link. There's quite a lot of work required to actually conclude that this function Sx is actually the equivalent to Pz. It doesn't just jump straight out at you. You see that we had to do the work. We had to first let z equal x plus 1 on x, and then later on we had to define ak, and it was then that we kind of were able to show, they are equivalent, so let's use this result. But even then, before all of that, just knowing proof by contradiction is the way to go. Maybe that doesn't jump out at everyone, but hopefully now that you've seen this, you kind of have in your toolkit, actually when I'm being asked to prove something about roots, common examples being that there's no real roots, or another one being no rational roots, think of contradiction and think, can I just assume the opposite and then get somewhere nonsensical like what we did here. Now there are a lot of steps in between to get there, and we had to be very careful, I would argue, with our inequality here, especially at this point, and making really clear that we knew what was going on and why we had to assume alpha is real to be able to do this. But from there you kind of end up with something that hopefully is clear. You can't square a real number and expect it to be negative. So there's our contradiction. So hopefully that all makes sense now, and you were able to follow along with all that. And yeah, tick boom.